This week's laboratory is all about Fourier series measurements with the spectrum analyzer. The key book material is Table 3-1, Fourier series signals, which details the calculations associated with the Fourier series for periodic or repeating waveforms. Remember, Fourier series allows one to break any periodic waveform into three components. 1. A DC or offset value. 2. A sinusoid at the fundamental frequency f0, which is defined as 1 over t, with t being the period of the waveform being analyzed. And finally, 3. Sinusoidal harmonics or integer multiples of the fundamental frequency. Not every waveform will contain all three Fourier series components, but waveform C, the half-wave rectified waveform, for example, does. The full table has three sections. Waveforms A to D are sinusoidally related signals, including full wave and half-wave signals. The second section, waveforms E to H, includes square wave and pulse type signals. While the third and final section, waveforms I and J, has triangle and ramp waveforms. There are many other waveforms, of course, for which Fourier series values can be calculated, but these are the most common ones. So how do we apply the table? First, we will look at a sample waveform, the sine wave without offset, waveform A, which contains only one Fourier series component, a sinusoid at the fundamental frequency f0, with an amplitude or magnitude value of A. To set up this signal, we will use a 0.5 volt or 500 millivolt peak-to-peak signal at 1 megahertz. The test setup is simply to connect the function generator to the oscilloscope. And we activate the signal output. We will see the signal displayed on the scope. 1 megahertz, 500 millivolts, peak to peak. Before we check the signal on spectrum analyzer, we need to review its setup screen without an input. When the spectrum analyzer is first turned on, or after pushing the preset button, the default settings are the following. The horizontal axis is a linear axis from the left-hand side of 0 hertz to 1.5 gigahertz or 1500 megahertz as the stop frequency. The vertical axis is a logarithmic power display with 0 dBm at the top and each division minus 10 dB. So minus 10 dBm, minus 20 dBm, all the way down to minus 100 dBm. Minus 100 dBm is a very small value of 1/100th of a picowatt. Because our signal is only 1 megahertz, we will first set the stop frequency to 10 megahertz. Press frequency, stop, 10 megahertz. The display we now see will be from 0 hertz to 10 megahertz. The signal that is currently being displayed is the zero frequency indicator. The zero frequency indicator is not a real signal, but it is put there as an aid to show us where the 0 hertz point is on the frequency. If we calculate the signal level in dBm for our 500 millivolt peak-to-peak signal at 1 megahertz. When we calculate the power for a 500 millivolt signal peak-to-peak, we calculate a value of 0.6 milliwatts, which is minus 2.13 dBm. So we should see a signal at 1 megahertz, 1 square to the right of the 0 indicator, and slightly below the top level of 0 dBm. When we connect the signal, we indeed see a signal right around the 1 megahertz point. Press the peak marker button and you will see the display. 1 megahertz and minus 8.08 dBm. The 1 megahertz is a good value, but the minus 8.08 dBm is not. It is a smaller value than we expected. We will solve this issue by going back to the scope to display the signal. We now see on the screen that the peak-to-peak amplitude is about 1/2 of what it was originally, 250 millivolts versus 500 millivolts. So what is causing the reduction in signal level by the spectrum analyzer? The spectrum analyzer is a 50 ohm device. This means that its input impedance is 50 ohms, not 1 megohms like the typical scope. This causes the signal to reduce in value by 50%. If we recalculate based upon 250 millivolts as a peak-to-peak signal, we actually get minus 8.13 dBm or minus 6 dB reduction. So now this is why we have the minus 8.08 value for our signal. One can easily confirm that it is the spectrum analyzer input impedance causing the reduction in signal level by removing the signal from the spectrum analyzer and monitoring the scope display. And we see the scope double in value back to the 500 millivolts peak to peak. But we cannot change the impedance of the spectrum analyzer, so we need to learn to deal with it. The primary way of dealing with the signal is simply to monitor on the scope and the spectrum analyzer at the same time. That way the values can be correlated between them. Returning to the spectrum analyzer display, we actually see more than one of our 1 megahertz signal. In this case, we see two other signals, much smaller in magnitude, but certainly related to the input signal, as when we remove the signal, they go away also. So, in order to examine those signals, we need to adjust the bandwidth control on the spectrum analyzer. Touch the bandwidth control and adjust the RBW, the resolution bandwidth, from 300 kilohertz down to a value such as 10 kilohertz. We now see a much more typical spectrum display with only terms at 1 megahertz and then successive terms. These terms, if we push the peak right button, we will see a marker indicate that that signal is at 2 megahertz, which is the second harmonic of our fundamental signal. And the next signal is at 3 megahertz, the third harmonic of our fundamental signal. These signals, though, are very much smaller than our original signal, on the order of minus 60 dBm, or almost 50 dB, or a power of 10 to the fifth smaller than our original signal. If the spectrum analyzer amplitude or vertical scaling is changed by pushing amplitude and log to linear, we see that in the linear mode, our 1 megahertz signal has declined, and the 2 and 3 megahertz signals are essentially zero. This is because they were only 100,000th or 1050 dB below the primary signal. We can now increase our signal until we get a larger value of amplitude. We'll increase it till we get close to 0 dBm. And when I come back, I see a 0 dBm signal. Now be careful not to increase the signal level too large. We hear the tone from the spectrum analyzer, which tells us that the signal level is too large. When you hear that tone, immediately disconnect or reduce your signal level. Now, if I return to the log mode, I will see my primary signal peak at 1 megahertz and slightly below 1 dBm. The harmonics at second and third have proportionally increased. So, that is the first measurements associated with the sinusoidal signal. The second signal we will look at is the triangle wave signal. We will return to an amplitude of 500 millivolts peak to peak and keep the frequency of 1 megahertz but change to a ramp or triangle signal. If we look at the analyzer, we will see again our peak signal at 1 megahertz, but we also see larger values at the odd harmonics, the third, the fifth, the seventh, the ninth. Record these values by using the peak and the next peak right value to record those values. Even harmonics will also be indicated, in this case 4 megahertz and 2 megahertz, the fourth and second harmonic. If we change the frequency display and the stop frequency to be 20 megahertz, we can see the harmonics actually increase even to the 19th harmonic or 19 megahertz. Increasing the stop frequency again to 50 megahertz, we can see that the harmonic content of the triangle wave continues out to essentially 30 to 40 megahertz until it drops so low that those values can be ignored. But harmonics will exist in the triangle wave theoretically up to infinity. In the laboratory, record harmonic levels at least to 10 to 20 megahertz if you can get good readings. Peak, next peak right, second harmonic, third harmonic, fourth harmonic, fifth harmonic, seventh harmonic, ninth, 11th, 13th, 15th, 17th, 9th. In order to look at the square wave, simply go back and press square wave on your generator. If we return to the spectrum analyzer,